We're going to continue our discussion with first-order differential equations using the method of separable variables, and we're going to apply this concept, this method, to an initial value problem. Here's another example of an initial value problem. You're going to have to recall some trigonometric identities as well as integration by parts. So let's say we're given this expression, e to the 2y minus y, take that quantity, multiply it by cosine x, and then multiply it by dy dx, is equal to e to the y sine of 2x. We have an initial value, y0 equals to 0. That's our initial condition, or initial value. Next, we divide cosine of x on both sides of this equation. So that leaves e to the 2y minus y divided by ey dy is equal to sine of 2x cosine of x dx. Again, we're using the method of separable variables, where we isolate on one side a single variable, in this case y, and on the other side we isolate into another single variable, and in this case it's x. Now we can simplify on the right hand side. E to the 2y divided by ey leaves ey, and then negative y over ey leaves negative y e to the minus y dy. There's a trig identity, sine of 2x, and we can express it alternatively as 2 sine x times cosine of x. Well, we see this cosine of x cancels out this cosine of x, so this leaves sine of x multiplied by 2. So this is what's left on the right side of this equation, and we're going to integrate both sides of this equation now. So here we'll integrate this later, but we'll focus now on the left side. We're going to do the integration by parts. So this is the first term here is easy to integrate. It's just simply e to the y, and so the integration of part will occur here. Now you define u is equal to y. dv will be e to the minus y dy, and that's expressed here, and we'll put a minus sign. So that's your u dv integral when you substitute it right here. Now v, we take this expression and we integrate this, is just simply e to the minus y, and then taking the differential on both sides of this equation yields du equal to dy. Now we do all the substitution that we defined here and substitute it in this expression. Now we note that u dv is once again this expression here, and that uv is defined here. Here's u and here's v. We're going to subtract this with this integral v, which is e to the minus y du, which is simpler to integrate. When we do that, we have, for the first term is just ey, and then this term right here consists of these two terms. Now this is the uv term, u against is y, and v is e to the minus y. So that's what this first term is. And then this term is a result of substituting for v right here and du for dy. So you can see that this is simpler to integrate. Now when we do that, we get e to the y plus y e to the minus y. So that's these terms, and then this term right here is just simply e to the minus y. When you integrate the right side, we just completed the left side. Now integrating the right side, we have that equal to negative 2 times the cosine of x plus c, where c is an arbitrary constant. Now we can get rid of this arbitrary constant by applying our initial value or initial condition here. In this case, at x equals 0, y is 0. So we'll just simply substitute that. Substitute y 0 here, 0's here, 0's here in this exponent, and 0 here in this exponent as well. So we substitute all the y here. Then we substitute x with 0. Cosine of 0 is simply 1. So here on the left side is 1 plus 0 plus 1 is equal to negative 2, because cosine of 0 is 1, plus c, and solving for c yields 4. Now we take this c and substitute it back into this expression, and we get e to the y plus y e to the minus y plus e to the minus y is equal to negative 2 cosine of x plus 4 is the solution to this differential equation.